Hello everyone. Today we will be discussing about one of the most important components of theory of computations course, Turing machines. This was the first machine which had reading, writing and processing capacity very much equivalent to modern day computer. If we talk about a standard Turing machine, it consists of 7 tuples where Q is a finite set of states, sigma represents a finite set of input alphabets, gamma represents a transition function, Q naught the initial state which is part of capital Q, F is the set of final or accepting states, delta is a blank symbol on the tape and tau is a finite set of tape alphabets. Input is placed on an infinite long tape in a Turing machine which is initially blank, and this is represented by all deltas. The most important component of the Turing machine is a read-write head. This head can read a symbol from the tape one cell at a time, write a symbol on the tape one cell at a time, and move either towards left or towards right after writing on a particular cell. Say for example, we have a transition from state Q1 to Q2 and it is represented by ABL. The tape has input AABB. The tape head is right now on A. So it will say read input A, write input B and move towards left. So this is how the transition will take place from Q1 to Q2. A has been read, has been replaced with B, and the read-write head has moved towards the left side onto the delta. If we want to represent the transition of right side, it will be represented by ABR. Read A, write B, and move one cell towards the right. Every regular language is a subset of context-free language, and every context-free language is a subset of Turing machines. So every machine which can be drawn through finite automata or push-down automata can also be drawn through Turing machine. Turing machine is deterministic. That is, we cannot have two outputs corresponding to a given input. Say for example, we are on state Q0 corresponding to state Q0. We cannot have two moves, one to Q1 and another to Q2 on single input A. We have compulsorily a deterministic machine that is corresponding to every input. We have only one output. Another important point is that there are no epsilon moves which are allowed in the Turing machine. A machine halts if there are no possible transitions to follow. Input is accepted if machine halts in a final state, and input is not accepted if machine halts in a non-final state or if machine enters a infinite loop. We will be discussing all three cases in the coming slides. Say for example, we have to draw a Turing machine for A star. That means at least one A followed by any number of A's. The input which we have on the tape is 4A. We start with the start state. We check first A. Corresponding to first A, we will convert it into delta and move right. This is the trace which is for the machine which is having the input AA. We show the symbol which is right now into consideration by coloring it with red color. Next, we move to one step right, that is to second A. As per the machine, since we get second A, we are supposed to convert that into delta and we will be on Q1 state itself and move towards right because it is A delta R. So the trace will be that second A has been converted into delta. There is another A. We are on Q1 state. We will remain on that step itself because there is a loop at Q1. Again, this A will be converted into delta and we will move towards right because we have A delta R. Now again, the trace will be that the third A has been converted to delta. We are left with only one A and we are on Q1 state. Corresponding to that, the transition says A delta R. So this is converted into delta and we move one step towards the right. When we get delta and we are on Q1 state, we are supposed to move to QF state by converting delta into delta itself and we have reached the final state. So here we can say that this is the state when we have accept and halt. We reach the final state after starting off from the Q0 state, that is the start state, and we have successfully halted the machine. Now we consider the case when the machine will reject the input. The input which is provided is A, B, whereas the machine which has been designed is for A star. When first A is encountered from start state, it moves to Q1 state and the trace is given. Next A, again it will have a self loop on Q1 itself. It will move towards the right. Now it moves again, third A, self loop of Q1, and it will again move towards the right. But now when we move towards the right, we come across B. On Q1 state, we don't have any move corresponding to input B. So this is how the machine will halt. It will be rejected and it will be halted. So this is how reject and halt state is encountered. Now we come to the third condition, that is a Turing machine with infinite loop. As per the machine, when the initial input is A on Q0 state, it will convert it into delta and move right. It has moved, that is fine. Now it comes across second AAR, that means read A, write A and move right. It will move towards next cell. After moving to this cell, the input is B and on Q1 state it is BBL. That means read B, write B and move left. Now it moves left. When it moves left, it again comes across AAR. That means read A, write A and move towards right. It comes across next B. It has BBL. That means now it is moving back to the initial A from where it started off. If it goes to A, it writes A and move towards the right, and this process will continue. It moves towards right, it moves to B. When it moves towards left, it moves to A. So this is a condition where it will go on moving in an infinite loop. So this is a state where we can say that it may be rejected or it may not be rejected. This is a TM with infinite loop. Now we come to TM for AN, BN. The objective is to design a Turing machine which reaches the final state if number of A in a given string is equal to number of B. How should we draw this machine? So that is what are the intuitions behind the design of this machine. Corresponding to every input on the tape, we should find a B and convert both of them to delta. Please remember, one of the very important points when designing a Turing machine is that delta is the marker to identify the endpoints of the inputs on both sides of the tape. So please never add delta in the middle of the input. In case you want to replace any symbol A or B, you can always replace with dollar sign, with asterisk sign, with ampersand sign or any sign, but please don't replace it with delta. Now the additions which we will follow is that we will first convert A, very first A on the tape with delta and try to find the B at the end of the tape to match with the first A. We do not convert the first B on the tape because if we could try to convert the first B, then we will get delta in the middle. So just check, this is the machine, first Turing machine corresponding to A and B and which we have drawn. We are considering this by having 2A and 2B, that is A to the power 2, B to the power 2. Now just see how this machine will function. We start with the start state, we find A, we convert it into delta and we move to Q1 state. This is the trace, A has been converted into delta. Next, we move to Q1 state. In Q1 state, we come across A. We don't change this A. We keep the A as it is. Read A, write A, move towards right. Next step, so the trace will be that A remains as it is. We move towards next input on the right. We come across B. We say if it is B, don't change it and move towards right. We now again move towards next move. We have B, no change, B, B, R, move towards right. This process continues until we go to the end marker on the right side, which is delta. The moment we come across delta, we keep it as it is as delta and we move towards left one cell. Now we have already crossed off 1A. We will shift this B to delta. Now the scenario at present is that we have converted first A on the tape to delta and last B on the tape to delta. Now we are left with 1A and 1B. We will again start scanning from the left side of the tape. So we need to move back. If we come across B, it will be remaining as B itself and we will be moving towards the left side. If we come across A, it will remain as A itself and we will move towards the left up to what point? Until unless we reach delta on the left side. Since delta is the end marker, we will not change it. Read delta, write delta and move towards right one cell. Now when we come to this, the next was A. So we are basically moving in the loop of Q0, Q1, Q2 and Q3, starting off with converting very left side A into delta and very right side B into delta. So we have converted this A into delta. We move one step right. We come across B, no change. Now we will shift towards delta. The moment we come across this delta, we identify that this is the end marker on the right side. So we will keep it intact and move one step left. When we move towards one step left, we will convert this B into delta. Now we have actually converted both A and both B into delta. Now we need to identify that this entire tape should be blank since we have converted both A into delta, both B into delta. When we look across, we identify that the entire tape is empty. We move one step right. We were on left side where we had no A left out. We move one step right. We see no B left out. So we will change this into delta and ultimately we have reached to the final state. So this is accept and halt. Please remember when we are moving towards the final state, we can write L oblique R. That means you can move towards left side or you can move towards right side. It hardly makes any difference. Now we will consider a case in which we have 2A and 1B and we will see whether the machine which has been designed for A and B and rejects this scenario or not. We will start with the start state, convert first A into delta, move right. We come across next A. We should not change it. In fact, we should keep on moving till we come across the right end marker on the tape. We will not change any A. A will remain intact. B will remain intact. We will keep on moving towards the right side. When we come across delta, that means we have reached the last point of the input on right side. We will not change this end marker, but now the moment we move towards the left, we should come across a B because we have already crossed off a A and now we should cross off a B. We will convert this B into delta and we will move towards left. On moving left, we will not make any change in small a or small b. They will remain intact. Try to move to identify where is the last or the end marker on the left side. The moment we come across delta, that means we have reached the end marker on the left side. And now without shifting, without changing it, we will move towards the right. We move towards the right, we come across A, we will convert it into delta and now we will start with the search for second B. Because we have already crossed off one A and number of A should be equal to number of B. Now we identify that instead of B, we come across delta. So that means we will move from Q1 state to Q2 state. On Q2 state, We have only one out move that is corresponding to B, but when we move left and we perform the read operation says that we have delta, but Q2 state says that it has no output corresponding to delta. So this is how reject and halt state has been reached. That means our machine has successfully identified that corresponding to double A, single B, this machine will reject. Now we move to the second scenario in which number of B is greater than number of A. First A converted into delta, and now we come across B. When we have small b, no change. It will remain as it is. We will move across without making any change in A or B, and we will try to identify the end marker on the right side. We come across the end marker, that is delta. When we come across delta, we will start moving towards the left. Since we have crossed off 1A, we will cross off 1B just nearest to the delta on the right side. We will convert this B into delta. We are now on Q3 stage. At this point, we come across B. We will not make any change, and we will try to identify where is the end marker on the left side. We get delta, delta, delta R. We will keep this intact and move towards right. Now we are on Q0 state. When we are on Q0 state, we come across input on the tape as B. Now just check, on Q0 state, we don't have any output corresponding to B. So that means we had one extra B which was remaining. All the A have been cancelled off with B, but we have one extra B which is left out. So we will reach the reject state in this. So that means the machine which we have designed for A and Bn has been proved to be valid if number of B is greater than number of A. Now we come to the second method of designing the same machine. What are the intuitions behind design of this machine? We will convert first A on the tape to capital A and try to find first B to match with first A and convert it into capital B. So likewise, we will keep on converting all small a into capital A and match with all small b into capital B. And in the end, if we come across such a point where all the A which were converted into capital A is equal to all the B which were converted into capital B, this means that number of A is equal to number of B. We are in Q0 state. We perform first read operation. We get A. We convert this small a into capital A and we move towards right. We will not convert second A because we want to find first small b on the tape. We get small b. We will convert this small b into capital B. We have converted first small a into capital A and first small b into capital B. So this is the trace for this particular move. Now we move towards left. If we come across small a, we will not change it. Now our end marker on left side is capital A. Small a remains unchanged and we have to move one step left. When we move one step left, we come across capital A. We will not change it. This is serving as an end marker for the left side. We move to Q0 state. Here we come across small a. We will convert it into capital A and we move one step towards right. Without making any change in capital B, we will move towards right in order to identify next small b. We come across small b. The moment we come across small b, we will convert it into capital B because we have already converted one small a into capital A. And corresponding to that, we need to convert one small b into capital B. We have converted this and we will move back. When we move back, we come across capital B. We will not change it. It will remain as it is. We come across capital A. We will not change it. This is serving as the end marker. That means up to this point, all the small a have been converted into capital A. We move to Q naught state. When we move towards right, we see that none of the small a is left out. Since none of the small a is left out, we need to identify that none of the small b is left out. So we have first capital B, it will remain intact, no change. We move towards right. We again find next capital B, that means it has already been cross-checked with one of the small a by converting it into capital B. Now we should not get any small b since we have converted all small a into capital A. We should have all small b converted into capital B. So when we move towards right and we get a delta, that means we have reached the end marker and there is no small a or small b left out. So this is a machine which is actually giving the right output corresponding to a and b, and that is number of a is equal to number of b. So we reach the accept and halt state. So this is the final trace for this machine, double A, double B. So we have discussed one of the very important components of theory of computations, Turing machines. In the coming slide, we will discuss few examples of Turing machines. Thanks.